Welcome back. In this section, we're going to begin talking about graphing polynomials. It's actually going to be a topic that's going to come back a couple of times during this chapter. To begin with, talking about zeros and roots of a polynomial, when I talk about a real zero or a real root, I'm talking about some x value that gives us a y value of 0 for our polynomial function. So, for example, if I'm thinking about a function like f of x is equal to x minus 1 times x plus 1, you can see that there would be two real zeros. One would be an x value of 1, that would make this 0, and a value of negative 1 would also make my polynomial equal to 0. Now, there's a couple of equivalent things that you could say, which is if you have an x value that's a 0, then that means it's a value that gives you a y value of 0, or in other words, you have that x-coordinate is the x-coordinate of an x-intercept. It's also true that if you are an x-intercept, then the x-coordinate must be a value of x that solves the equation, where is this polynomial equal to 0? And if that's true, if x equals c is a solution, that means that x minus c needs to be a factor. And being a factor means that you go in evenly with no remainder. So you could also say that if you take x minus c and divide that into f of x, it should go in with a remainder of 0. So you actually have 5 equivalent things that you could say about that. So if we're thinking about that polynomial that I had just had up, x minus 1 times x plus 1, you could say, for example, that since x equals to 1 is a 0, because it makes the polynomial equal to 0, then that means 1, 0 is an x-intercept, which means x equals to 1 is a solution for where is this polynomial equal to 0. That also means x minus 1 is a factor. It also means that x minus 1 can be divided out of this polynomial and leave a remainder of 0. Now, to use this idea here, we want to create a polynomial function with some given zeros. First, I want it to be a degree 3 polynomial, and I want its zeros to be 1, negative 1, and 2. So, firstly, I can say that, well, if I want 1 to be a 0, that means x minus 1 needs to be a factor. And if negative 1 is a 0, then x plus 1 needs to be a factor. And if 2 is a 0, then x minus 2 needs to be a factor. So f of x is x minus 1, x plus 1, x minus 2, all multiplied together. That's one solution. And you can quickly check to see that this has degree 3. If you were to expand this out, and if you wanted to know what the leading term is, remember the leading term would be the leading terms for the factors themselves multiplied together. X times x times x, which is x cubed. So leading term is x cubed. That's a degree 3 polynomial, and it does have the 3 zeros that we were asked to give, 1, negative 1, and 2. Now, you might have noticed that I've left a gap here in front of the start of my function, and that's because there's the second follow-up question. Is there more than one possible answer to this question? And the answer is a big yes. In fact, not just is there one or two more possible solutions, there's actually infinitely many solutions. Because if you take this polynomial that I've created and, let's say, multiply it by 2, that would give you a vertical stretch of that graph, but that wouldn't change the location of the x-intercepts. The x-intercepts would still be 1, negative 1, and 2, which means it would still have the zeros of 1, negative 1, and 2, and it would still be a degree 3 polynomial. And that's true whether you multiply it by 2, or 3, or 7, or whatever number you'd like. And you, of course, could also multiply it by something negative. This would flip it in the x-axis as well as stretch it. Again, you would still have the same zeros as before, so this would be yet another example of a degree 3 polynomial with those given zeros. So I guess the important thing to take away from this is that zeros are important for describing a polynomial, but they're not everything. There's something else that we need to know before we'll be able to graph polynomials. So one of the things that we'll need to talk about is what happens if you have a factor that's repeated, or in other words, what happens if you have a repeated zero. So when you've got a factor that shows up more than once, then the zero for that factor is a repeated zero. So if we're looking at the example that I have here, f of x, you can see that there are three different zeros. If we wanted to know what the zeros are, that's us looking for the x-intercepts, looking for where this function is equal to 0. And we'd find, well, either 3x squared is 0, or x minus 2 is 0, or 3x minus 1 cubed is 0. And then we could solve for what x needs to be. And we'd find that x is 0, x is 2, or x is a third. Now, the thing to notice here, of course, is when I say that x equals 0 is a 0, that came from 3x squared. That's actually two factors. That's x and also another x. That x was repeated twice. That means that this 0 has multiplicity of 2. Similarly, this x being a third, that was a factor that came, that was a 0 that came from 3x minus 1 being 0. And in our polynomial, we had 3x minus 1 cubed, which is really a 3x minus 1 times a 3x minus 1 times a 3x minus 1. So in other words, that's something where it has multiplicity 3, because 1/3 is actually a 0 3 times. And then finally, for the last one, x minus 2, that factor only showed up once, which means x equals to 2. That's a 0 that only has a multiplicity of 1. Now, the nice thing is that for polynomials, the multiplicity tells us something about how the graph looks. If you have a 0 with even multiplicity, then the graph just touches the x-axis and doesn't cross through. So with even multiplicity, we will touch the x-axis at that 0 and then go back in the direction that we came from. That would be an even multiplicity. On the other hand, if your 0 has odd multiplicity, then you don't just touch the x-axis, you cross through the x-axis. So if we have a 0 with odd multiplicity, then we will not just touch, we will cross through to the other side. And so that's enough information, hopefully, to be able to get a good idea on how our graph looks. It's not everything, there's still something else that we'll need, but that's at least a good start. So for this function, f of x, if we're looking for what its zeros are, we'd be looking for where is f of x equal to 0. And of course, x minus 5 times x minus 6 squared times x minus 7 cubed, where is that equal to 0? Well, at x being 5, at x being 6, and at x being 7. So if we're going to make a little table here, our zeros are 5, 6, and 7. And if we're listing our multiplicities, for x being 5, x minus 5 only showed up as a factor once. So x being 5, the multiplicity is 1. X minus 6 showed up as a factor twice. So x minus 6, since that showed up as a factor twice, that means 6 is a 0 with multiplicity 2. And similarly, x minus 7 cubed, that means that 7 is a 0 with multiplicity 3. And now for our behaviors at the x-axis, because x equals 5 has a 0 with odd multiplicity, that means it crosses the x-axis. Because x equals 6 has multiplicity 2, then we don't cross, we just touch the x-axis. And for x being 7, since that's an odd multiplicity, we cross the x-axis. Okay. One other thing just to mention, and this is something that we're not unfortunately going to be able to plot on our graphs, are the turning points. Turning points for a polynomial or for any function, those are the places where we change direction. That's why they're called turning points. Those would be the places where we change from increasing to decreasing, or decreasing to increasing. Places like this and that, those would be relative maximum and minimum values. Now, unfortunately, except for parabolas, we don't have the ability to find the location of those turning points. For a parabola, those turning points, that would be the vertex, and that's easy enough for us to find. But once we get beyond parabolas, once we get beyond a second-degree polynomial, the locations of those turning points are difficult to find. So that means that when we're graphing things, we might know, for example, that we cross through the x-axis and cross through the x-axis again, but we won't be able to tell where exactly in between those two x-intercepts the turning point has to be. We also won't have any idea how high up along the y direction the turning point would need to be. So just be aware of that we're not going to be labeling things as wonderfully as we might like. There are things that we would like to know, the locations of the turning points, but you actually need calculus skills to do that. And in fact, that's a major part of what you'll learn in calculus, how to locate those maximum and minimum values. Now, there is a nice little fact here for the relationship between the degree of a polynomial, the zeros, and the turning points. So first, if you have a polynomial of degree n, then that means you can have up to n different factors when you factor that polynomial, which means you can have up to n different real roots. You could have less than that, so you could have a degree 10 polynomial, for example, that only has one real root. Or you could even have a degree 10 polynomial that has no real roots. But it's impossible, for example, to have a degree 10 polynomial with 11 real roots. That definitely is impossible. So however many real roots you have, there's a limit on the degree that your polynomial could be. And so that also means, for example, if you knew that you had 5 different real roots, that your polynomial would need to have degree of at least 5. If you're going to have at least 5 real roots, that means you're going to need to have at least 5 factors, which means you're going to have a degree of at least 5. So just from a graph, we can put a little bit of a restriction on what our degree for our polynomial would need to be. The other nice thing here is for the turning points, even though we can't find them, that also places a restriction on the degree of our graph, or the degree of our polynomial. So if your polynomial has degree n, then the maximum number of turning points that you could have is n minus 1. And the reason for that is if you have, for example, a degree n polynomial, you can have as many as n different x-intercepts, and those maximum and minimum values would happen between those x-intercepts. So however many x-intercepts you have, so in this case I've drawn 4 x-intercepts, you can have as many as 3 turning points in between those x-intercepts. So if we're taking a look at this graph and we're wondering what's the minimum possible degree for this polynomial, then there's two things that we can look at. One would be the number of x-intercepts. I know, number one, that there are two x-intercepts, so that means the degree definitely needs to be at least 2, for sure. And that's because I know that for a degree 1 polynomial, you can have at most 1 x-intercept, so this can't be degree 1, this has to be degree 2 or higher. The other thing that we know is we've got 3 different turning points. I have a turning point here, here, and here, which if I have 3 turning points, then that tells me that I must have that the degree needs to be at least 4. And because we know for a degree 4 polynomial, it can have up to 3 turning points. A degree 3 polynomial can have up to two turning points. So this couldn't be degree 3. It also couldn't be degree 2 because degree 2 would only have 1 turning point. So if we're putting together our clues, because there were 2 x-intercepts, we said, well, the degree needs to be at least 2. There were 3 turning points, so that said that we needed to have a degree of at least 4. So bare minimum, the smallest possible degree for this polynomial would be degree 4. So I would say that degree 4 is the smallest possible. I won't be able to come up with an upper guess as to what the maximum possible degree is, and that's because there is no upper limit to the maximum possible degree. Things with much higher degrees than 4, so if you have polynomials of degree 12 or 30 or 1,000,000, it's possible to have those with only 3 turning points and 2 x-intercepts. So we can't really give an upper limit to what's the maximum possible degree, but we can say what the minimum possible degree should be, and that should be degree 4. If you had degree 3, then you wouldn't be able to have 3 turning points. If you had degree 2, you wouldn't be able to have 3 turning points. If you had degree 1, you wouldn't be able to have 3 turning points or 2 x-intercepts. That would all be completely impossible. So the only way that you could have 3 turning points and 2 x-intercepts would be if your degree was 4 or larger. All right, the last thing to mention is that we need to know something about the end behavior of our graph. The end behavior is what happens on the far left and far right. And the reason we need to know that is because if we have, for example, 2 x-intercepts, and let's say they both had odd multiplicity so that we knew that we crossed through the x-axis for both of them, then there's 2 basic shapes. You could start from above, cross and end heading upwards, or you could start from below, cross, and head downward. And both of those would be graphs of functions that have 2 zeros that are both there at those locations with odd multiplicity. The difference between them is that the graph that I sketched in black ends up going to positive infinity on the far left and far right, while the one that I sketched in blue ends up going to negative infinity on the far left and on the far right. So for us to be able to sketch our graph, we need to know not just what's happening at the x-intercepts, but what's happening at the far left and far right. We need to know what the end behavior of our graph is. And the nice thing is that the end behavior for our polynomial is going to be the same as the end behavior for our polynomial's leading term. So, for example, if you were looking at graphing this polynomial, 7x cubed minus 2x plus 1, you want to know what is the end behavior. The end behavior would be the same as its leading term. Its leading term is 7x cubed, and we know for the cubing function, 7x cubed would go up to positive infinity on the far right and go down to negative infinity on the far left. And that means that this polynomial, 7x cubed minus 2x plus 1, would do the same thing. It'll do whatever it does in the middle, but on the far right it will go up, and on the far left it will go down. So let's do one last example here, and then we'll have ourselves a little bit of a pause. This is kind of a refresher from 3.2. We did some of this already, finding leading terms and finding the degrees of our polynomial when it's in factored form. So let's do that now. Let's start off with our leading term, which we get by multiplying the leading terms of all of our factors together. So our leading term for the first factor is just 3. For the next factor, 3x minus 1, its leading term is 3x. For the next factor, x plus 1 squared, the leading term is x. But since it's x plus 1 squared, then it's really x and another x, or x squared. For our last factor, we have 2x minus 3 squared. 2x is the leading term, and 2x minus 3 shows up twice, so 2x times 2x. And then now we just need to multiply all of this together to say what we have. And what we have would turn out to be 36x to the 5. So that means you know the degree of this polynomial is degree 5. While I'm here, just to mention the constant term, I didn't ask for it, but I could ask for it. Constant term we'd find by multiplying all of our constants together, all of our constant terms for each of our factors. So that would be the 3, the negative 1, the positive 1, and the negative 3. And of course, the positive 1 was from x plus 1 squared, so constant term is squared. 2x minus 3, the constant term is minus 3, and 2x minus 3 is squared. So we would have our constant term of negative 27 if we were to multiply that out. That tells you, of course, just as a little side note, that if we were graphing this, that we would have a y-intercept of 0, negative 27. Remember, that was from something back in 3.2. We said that one of the nice properties for polynomials is that whatever the constant term is, that is the y-coordinate for the y-intercept. So for this polynomial, we already have one point. It passes through the y-axis at y being negative 27. Okay, so that's neither here nor there. The question that we really wanted to address, though, was what is our end behavior? And so for our end behavior, that would be the same as the behavior of its leading term. Remember, the end behavior is just what's going on the far right and on the far left. And we know that this is an x to the 5 kind of a shape multiplied by a positive number. So this is doing the usual odd power of x thing where it goes up on the far right and goes down on the far left. And now we're going to take a pause here, and when we come back in the second half of this lecture, we're going to put all of the clues together: the behavior at x-intercepts, the location of the y-intercept, the behavior at the far left and far right, in order to graph some polynomial functions.